let's get started. Our first speaker today is Frederick Lindsten. He's going to talk about graphical model inference, sequential Monte Carlo meets deterministic approximations.
Okay, thank you very much for the introduction. Good morning, everyone. So first of all, this is joint work with Joni Helske at Linköping University in Sweden and Matti Vihola at the University of Jyväskylä in Finland. Okay, computational algorithms for approximate Bayesian inference are at the core of many machine learning problems. Such algorithms are often divided into two groups. On the one hand, we have various deterministic methods such as variational inference, approximate message passing, etc. And on the other hand, we have sampling-based algorithms such as Markov chain Monte Carlo and sequential Monte Carlo. These types of methods both have their pros and cons, so a natural idea is to try to come up with methods that are somewhere in the middle that can take advantage of the strengths of both types. Recent examples of this include variational SMC and variational MCMC, and as you can guess, the method that we propose in this paper also belongs to this middle ground. To be a bit more precise, we consider inference in probabilistic graphical models expressed as factor graphs. And this is a general way of encoding or describing dependencies and structure in probabilistic models. So given such a graphical model, the task at hand is to compute the joint distribution pi, which can be written as a product over the factors of the model, fj. And furthermore, it's often of interest to estimate the unknown normalizing constant of this model, Z. Our starting point for solving this problem is to use the sequential Monte Carlo method that was presented at this conference a few years ago. And the basic idea behind this SMC method is to decompose the graphical model into a sequence of subgraphs. We can then define an intermediate target distribution gamma for each of those subgraphs, and then sample from these gamma distributions in turn using an SMC algorithm until we recover the full graph of interest. A limitation of this method, however, is that it does not take the dependencies on future variables into account at these intermediate steps, and this can degrade its performance. So to mitigate this, we propose to modify the intermediate targets by introducing so-called twisting functions, psi. And these twisting functions can be seen as a type of look-ahead, which allows us or helps us to take these dependencies on future variables into account throughout the SMC sampling. In fact, we show that if we select these twisting functions according to this equation, then the resulting SMC algorithm will output IID samples from pi, and its normalizing constant estimate will be exact with probability 1. Now, clearly that is a bit too good to be true, and the problem, of course, is that computing these optimal twisting functions psi star is just as difficult as solving the original inference problem. However, this is where the use of deterministic approximations comes into play, because we can use such methods to approximate psi star and then use the approximate twisting functions within our SMC framework. And importantly, the approximation error here will only affect the efficiency and not the asymptotic consistency or the unbiasedness of our SMC algorithm. And we can therefore view our resulting method as a type of post-correction of the biases associated with the deterministic method of choice. So to illustrate this, we consider, or we show explicitly in the paper how we can use three popular methods to approximate these psi star, namely loopy belief propagation, expectation propagation, and Laplace's method. We also illustrate numerically on three examples the improvements offered by these methods for our twisted SMC. And if you want to see exactly how big those improvements are, you should come visit our poster at screen number 51. Thank you for listening.
Our next speaker is Francisco Locatello. He's going to talk about boosting black box variational inference.
Thank you for the introduction, and thank you everyone for being here. I'm really glad to present our work on boosting black box variational inference. This is joint work with amazing colleagues, Gideon, Rajiv, Isabel, and Gunnar. So variational inference is a method to approximate an intractable posterior distribution, which involves solving a constraint optimization problem in which one fixes a family of distributions, Q, and then aims to find this distribution in Q as close as possible to the target posterior by minimizing a KL divergence. And there is an inherent trade-off between the tractability of the problem and how expressive the family Q is. So here you can see a simple example in which we use a single Gaussian to approximate a mixture of two Gaussians. And this is particularly troublesome because our variational approximation is placing a lot of mass on an area in which the target posterior actually has low probability. So the issue here is that variational inference does not give you the option to trade additional runtime effort for a better approximation. So if something like this happens in practice, I cannot just run variational inference a little bit longer and get a better solution. So to solve this limitation, boosting variational inference has been recently proposed at the intersection of the Bayesian and the convex optimization communities. From an optimization point of view, boosting variational inference still minimizes a KL divergence, but now we consider the convex hull of the family Q, which means that we allow the solution to be a mixture of densities from Q. And note that although this problem is much harder than the original one, we can solve it iteratively by adding a family member of Q at a time. So we studied this problem from the lens of the Frank-Wolf optimization framework, which we already linked to boosting variational inference in our previous work, providing novel theoretical understanding. And to use this result in variational inference, we had to introduce several assumptions and sufficient conditions for convergence. And the consequence is that practitioners is required to have intimate knowledge of the design of the optimizer, and in particular of the linear problem that we solve at every iteration. And indeed, these modeling choices must crucially satisfy the assumption for the algorithms to converge. So the drawback of the previous work is that despite providing interesting theoretical guarantees, the final algorithms are hardly practical. So in this work, we take a very different approach by relaxing some of the assumptions that we previously made and propose a new theoretically grounded subroutine for boosting variational inference, which is also very practical because it can be implemented with a black box variational inference solver. So this is roughly how it works. So with boosting, we turn inference into an iterative procedure where we build richer and richer approximations of the posterior over time. And each iteration, the boosting subroutine minimizes a KL divergence here on top. And the target depends on Qt, which is our current approximation. So at each iteration, we add a new component into the mixture, which is the convex combination, to improve the fit. So instead of approximating the posterior directly at every iteration, we approximate this term here on top, which depends on the ratio between the posterior and our current fit, Qt. And the final solution is guaranteed to be an approximation of the original posterior. So to understand our boosting subroutine, we take the elbow of this divergence, which we call the relbow, residual elbow. And here you can see two terms. One is roughly the regular elbow, depending on the choice of lambda. So for example, if lambda is equals to 1, you have the normal elbow. And the other term is pushing the next component as far away as possible from the current approximation, Qt. So we want to push the new component as close as possible to the target posterior and as far as possible from our current approximation, hence the name residual elbow or relbow. And we have many different experiments in the paper, including real-world medical data, a variety of Bayesian models and variational families. And the experiment shows that the method indeed works, as promised. And here I just want to show you the sanity check plot to show that we are indeed able to approximate bimodal distribution. And it's very easy to use this algorithm because the optimization approach is independent from the specific probabilistic modeling choices. So as one would do in Edward, one just define a model and then run the inference algorithm. And the only difference is that now the inference algorithm is wrapped in a for loop, and each iteration you iteratively approximate a different distribution and build a richer approximation of your posterior. So thank you very much. I hope to see many of you later at our poster, number 38. Also look at our Edward code, which you can use out of the box to reproduce our experiments and to obtain richer posterior approximations on your specific problems. Thank you.
Our next speaker is Trevor Evans. He's going to talk about discretely relaxing continuous variable for tractable variational inference.
I'm Trevor Evans, and this is a short presentation on discretely relaxing continuous variables for tractable variational inference. This is joint work with Prasanth Nair, and we're both from the University of Toronto. So having the ability to perform efficient inference is extremely important. For example, memory and energy efficiency are very critical for mobile devices where we would often like to perform real-time inference in this hardware-constrained environment. Additionally, large-scale deployed models need to be evaluated billions of times, and this can incur substantial energy costs that we would like to minimize. So we introduced a new technique to perform approximate Bayesian inference with discrete variables. And this has the ability to dramatically reduce computational requirements at inference time. So continuous priors are typically used for approximate Bayesian inference, and this is largely due to the fact that there is several computationally tractable training strategies, for example, using the reparameterization trick. However, discrete priors are very difficult to train, but they offer many advantages at inference time since the posterior samples will be sparse and low-precision quantized integers. So we introduce a variational inference technique that enables extremely fast and efficient training with discrete priors, allowing us to discretely relax these continuous priors. So the reason training discrete models is challenging is because the size of the discretized hypothesis space increases exponentially with the number of variables in the model. And this is a problem because the elbow, which is our training objective during variational inference, requires evaluating the log likelihood at every single one of these points in the hypothesis space. And this obviously quickly becomes intractable. So for this reason, we typically resort to stochastic estimators, and available estimators for discrete models tend to be very high variance. So we, on the other hand, compute the elbow exactly. And we do this by viewing the log prior, log likelihood, and variational distributions at each point in the hypothesis space as entries into a b-dimensional tensor, where b is the number of variables in your model. So we then identify and exploit a low-rank structure that exists on some likelihoods, and this allows us to rewrite the elbow in a very compact form. And interestingly, this compact form, when we evaluate the elbow in this compact form, the cost is independent of the number of training points. So this allows the technique to be scaled to very large problems. So we call this the direct approach. And while it's not practical for all likelihoods, we identify a couple of models that are practical. For example, the class of generalized linear models. So obviously, since we've eliminated variance, our approach greatly outperforms reinforce, which empirically tends to have a very high variance and slow convergence. Additionally, we can compare a model with a continuous prior using the reparameterization trick to our direct model with discretely relaxed prior. And what we find is that often on many experiments, the direct model can outperform the continuous model with reparameterization on many data sets, both in terms of training time and test performance. And in addition, we have the advantage that our posterior samples are sparse and low precision quantized integers. So to summarize, the direct approach can exactly compute elbow gradients, and this is the advantage of eliminating variance and allowing the use of quasi-Newton optimization methods. Its training complexity is independent of the number of training points, which allows the approach to scale to large data sets. And the posterior samples consist of sparse and low precision quantized integers. So finally, in our experiments, we demonstrate accurate inference using extremely low precision 4-bit quantized integers. And we are able to train our model on data sets as large as 2 million points in just seconds, even though the elbow would naively require summing over a number of log likelihood evaluations equal to the number of atoms in the universe raised to the power of 30, which would be completely intractable to do naively. So we demonstrate the approach for mean field variational inference as well as for unfactorized variational distributions. The code is available online, and if you're interested, please visit poster 39.
Our next speaker is Michael Figanov. He's going to talk about implicit reparameterization gradients.
Hi, my name is Michael Figurnov. This joint work with Shekhar Mahab and Chandrimnik called implicit reparameterization gradients. Reparameterization gradients are one of the core tools in many modern probabilistic methods, such as variational autoencoders and automatic variational inference. Fundamentally, they allow us to perform backpropagation in graphs which have continuous random variables. Suppose that our cost function is an expectation of a function f over a random variable z. Using reparameterization, we can push the derivative with respect to the random variable's parameters phi inside the expectation and then apply the chain rule. However, computing the dz over d phi quantity requires a tractable inverse transformation, which is only available for distributions such as normal, logistic, and few others. In this work, we show how we can extend it to other distributions using implicit differentiation. As examples, we consider gamma, the conjugate prior for normal precision, and von Mises, an important distribution on the circle. Let us denote the cumulative density function, or CDF, of our distribution by capital F. Its key property is that it transforms our random variable into a uniform random variable. In standard or explicit reparameterization, we invert this process by first sampling a uniform random variable and then passing it through the inverse CDF. The gradient dz over d phi is computed by automatically differentiating the inverse CDF. But what if the inverse CDF is intractable? In implicit reparameterization, we decouple these two steps. First, we sample z using any sampling method, such as rejection sampling. Then, for the gradients, we use an alternative expression which does not involve the inverse CDF, but instead involves the derivative of the CDF with respect to the parameter and the density of the random variable. The derivation is 3 lines. Come to the poster if you want to learn the details. It uses implicit differentiation. However, the derivative of the CDF with respect to the parameter is often not implemented in the commonly used numerical libraries. So how can we compute this quantity? We notice that the CDF is often computed using a series expansion, such as Taylor series. So it is very easy to automatically differentiate the code for the CDF with respect to the parameter. We find that this approach performs best in terms of both speed and accuracy. As a baseline, we consider the finite difference approximation to this derivative, but find that it is orders of magnitude less accurate. A concurrent work of Yankovic and Obermeyer proposes a closed form approximation to the derivative, but it is not as fast and accurate as the automatic differentiation approach. An older work by David Knowles performs approximate explicit reparameterization, which is not numerically stable and because of that quite inaccurate. What can we do with this tool? As one application, we consider variational autoencoders. The standard normal prior causes the latent codes to concentrate around the origin. As an alternative, we consider a 2D torus latent space with a uniform prior and von Mises posterior. We see that the learned latent codes tile this space nicely and uniformly. In the paper, we also consider training of the latent Dirichlet allocation topic model. So to conclude, we have presented a more general view of reparameterization gradients. Our key insight is that we can decouple sampling from gradient estimation. Using this idea, we propose reparameterization gradients for a number of distributions, including gamma, von Mises, beta, and Dirichlet. Our method is faster and more accurate than the alternatives, and it's also easy to use because it's now implemented TensorFlow probability. On a more general note, we hope that this work allows us to move away from making modeling choices for the reasons of computational convenience. Thank you. Our poster is number 33.
Our next speaker is Chang Liu. He's going to talk about variational inference with tail adaptive F divergence. So we'll take questions and then end his talk.
HDMI. That's USB-C. Oh.
Okay. Okay, thank you very much. I'm Chang Liu from UT Austin. So this is a joint work with my students, Diling Wang and Hao Liu. So Hao Liu is actually an undergraduate intern in my group. So as many of the talk in this session implies, importance, variational inference is obviously a very important algorithm engine for solving lots of challenging problems, ranging from deep learning and reinforcement learning these days. One of the key challenges, however, is that typical variation inference tends to underestimate the uncertainty, especially for highly multimodal distributions. So in this case, variational inference, in many cases, tends to miss important modes. In this work, we propose a new variational inference algorithm based on a new type of what we call tail adaptive F-divergence. So this algorithm has the nice property of promoting mask covering without sacrificing robustness. So I will explain what this means in this talk. And then in the end, we will give a very simple algorithm that can be easily code up just in 5 minutes or so if you already have a code of variation inference. So definitely give a try if you are interested. So here's a very brief introduction of variational inference. So basically, the problem is we are given some highly complex distribution, which is P. It's typically the posterior distribution in Bayesian inference. And then we want to approximate P using a family of simpler distributions, Q theta, right? So Q theta could be Gaussian or Gaussian mixture, or normalizing flow, or other implicit models. So here we do the approximation by minimizing the KL divergence. It turns out the KL divergence is so nice so that this optimization can be performed tractably. Now, it turns out that KL divergence is not the only choice for variational inference. So there has been a lot of research showing that in some cases, using what's called alpha divergence is actually much better in many cases. So here, alpha divergence is a generalization of KL divergence by replacing the log function KL with this power function. So alpha is a parameter. The different choice of alpha will reduce to different special cases. So if alpha equal to 0, it reduces to the standard KL divergence. If alpha equal to 1, it reduces to the other KL divergence with a different ordering. And then alpha equal to 2 is chi-square and many other examples, right? So one of the motivations to use alpha divergence over KL divergence is that if we use very large values of alpha, it has the nice property of promoting what's called mask covering. What that means is if P is a multimodal distribution, then minimizing alpha divergence with large alpha will promote the Q distribution to cover all the probability density. So here in the graph, we show the example when we have a Gaussian mixture for P and the Gaussian for Q. But in practice, we can use fairly flexible Q theta. These days we can use mixture models, we can use normalizing flow. So Q theta could be very flexible. In this case, it's really helpful to have the objective function to promote stronger mask covering in order to achieve better approximation. As the last spotlight suggested, repartition trick has been really useful, and this is one of the reasons nowadays we can actually optimize over fairly flexible Q theta family. So it turns out we can perform stochastic optimization over general alpha divergence by writing down this formula of gradient. It's expressed in expectation under Q theta, and then we can approximate this gradient stochastically by drawing sample from Q theta. So here is a very nice formula. If alpha equal to 0, it reduces to standard variational inference with the repartition trick. If alpha is large, then we have the property of promoting mode coupling. So the story is very nice so far. Unfortunately, it has some problem. So one of the fundamental problem is that if you use a very large alpha, then the variance of this density ratio is going to be huge, right? So, and that means the variance for the gradient estimation is going to be high, sometimes even infinite. And I think even what's more problematic is that if alpha is even larger, then you can even get infinite alpha divergence as well as infinite gradient. That means not only you cannot approximate the gradient, it is that this whole problem is not well defined. It's fundamentally, there's some fundamental problem here if you use really large alpha. So you may think infinite mean and variance doesn't appear very often in practice, but it's not true in this case. It turns out here we have a very simple example. If you have two different Gaussian distributions, Q and P are Gaussian, and if the variance of Q is smaller than P, then you can find the threshold alpha star, such that if alpha larger than alpha star, you will have infinite mean. That means alpha divergence is not defined for that case. And if alpha is larger than alpha divided by 2, then you will have infinite variance. That means estimation is very difficult, right? So in this case, we need to have some way to kind of understand what's the value of alpha and how to adaptively adjust your alpha so that it matches with the kind of difference between P and Q. So a way to kind of mathematically understand this threshold and this infinite mean and variance is to use what's called a fat tail distribution. It turns out in the case when Q is more concentrated in P, the density ratio tends to perform distribute like as a fat tail distribution. This means the tail probability, which is the probability of the density ratio larger than some threshold, is approximately decay according to a power law. So, and here the alpha star is called the tail index. It's exactly the threshold we showed earlier. It is the upper limit of the finite moments, right? So alpha star is the maximum possible alpha divergence you can possibly define it, right? So, and ideally, we hope if we want to promote strongest possible mode covering, we want to find alpha star. Unfortunately, alpha star depends on P and Q in a very complex way. As Q changes, alpha star will change across the iteration. And alpha star, as the tail index, is actually fairly difficult to estimate from the sample. So that's a whole literature in statistics talking about how to estimate the tail index, but essentially the problem is actually very difficult. So now in this work, we have a kind of way to kind of avoid estimating the tail index by instead estimating the tail probability directly. So record that tail probability equals to the T power minus alpha. That's the decay, power law decay. Now if you take the inverse, then the inverse of the tail probability actually exactly equal to T power alpha star. So this is exactly the power function for the maximum possible alpha divergence, right? And what's nice is that the tail distribution is actually fairly easy to approximate. It can be easily approximated as an average of indicator functions, which is essentially given a set of sample, you can just find the rank of T in the sample, and that's your tail probability, right? So our idea then is instead of using a power distribution, we can use the alpha, the inverse tail distribution. This allows you to dynamically adjust the magnitude of alpha according to the tail probability of P and Q, P divided by Q. So let's do this. Let's try to approximate, replace the alpha by tail probability, right? But because the tail probability is not a power function, so we need to generalize alpha divergence. This turns out we need to use what's called F divergence. It's a generalization of alpha divergence, which replaces the power function with an arbitrary convex function, strictly convex function. By Jensen's inequality, you can easily show this guy is always larger or equal to 0 and equal to 0 if and only P equal to Q, right? So, and we can also derive a very similar gradient formula. It turns out in this case, we replace the weights, the power function in in alpha divergence with a gamma function. So this gamma function is the second order derivative of the convex function t, f, times t squared, right? So it's always a positive function. So now, in order to incorporate tail probability into the f divergence, one of the key observations is that because the second order derivative the second order derivative of f could be arbitrarily could be an arbitrary positive function. So if we can specify an arbitrary positive function over gamma, then that will reduce back to some valid f divergence, right? Because our goal is actually minimizing the f divergence, what we only need is to calculate the gradient. We don't actually need to go back and calculate the f divergence, so that it makes sense to just define whatever good gamma that you think is proper for your optimization purpose. So now this reduces to our main algorithm. Essentially, we have this very general gradient formula. If gamma equal to 1, it's the standard variational inference. Gamma equal to power, it's alpha divergence. Now we just take gamma equal to the inverse of the tail probability. That naturally just allows us to adapt the tail with the density ratio distribution. And this also helps to keep the finite mean, but also promotes the strongest possible mode covering. So here's an example. We randomly generate a Gaussian mixture. Starting from the left of the figure, we have the case when P is exactly Gaussian. In this case, all the algorithms approximate P closely. But then if Q becomes highly multimodal, it turns out all the standard algorithm tends to degenerate, while our algorithm actually stays stable. So here, for the approximation family, we actually make sure that the Q theta actually have more components than P. So theoretically, if we solve the optimization globally, we should be able to find exact approximation. But just because of the randomness and the property, the disadvantage of the divergence, we find the standard algorithm doesn't work as well as our method. So here we have more experiments on Bayesian networks, and we find our methods performs much better than any of the fixed value of alpha. So, and we can see that there's no single alpha that outperforms all the algorithms. So here we apply our methods to improve reinforcement learning. In particular, in this case, we can see what's called a soft actor critique. It's a policy optimization algorithms that leverages a type of KL minimization, KL divergence minimization for optimizing the policy. So here we just treat the policy optimization as a variation inference methods, and then use our method to improve this reinforcement learning algorithm. Turns out our improvement is actually quite significant. So here's the conclusion. We propose a new tail adaptive F divergence. It gives a fairly simple and efficient algorithm that just outperforms standard methods with a very simple modification of the code. Welcome to our poster then. Thank you.
Thank you. Any questions from our audience? Please walk to the mic if you have any questions. Okay.
Thank you for your talk. So how many samples do you need to estimate this tail distribution?
How many times?
How many samples you need to estimate this tail distribution?
The sample will be just the mini batch size in practice. It would
Okay.
be, yeah.
You basically just share the samples across time, or like?
No. So every iteration, we just sample a mini batch, a set of samples, let's say 100, and then use that to approximate the tail distribution. Because essentially, when in practice, the tail distribution, when you calculate on the sample, is really just calculating the rank. So in practice, you just calculate the rank of the samples and use the rank as a weight.
Okay, thanks.
Yeah.
Okay, due to the time constraint, let's take the question offline. Thank you. Our next speaker is Yaping Xie. He's going to talk about mirrored Langevin dynamics.
Okay, so good morning, everyone. My name is Yaping. This is a joint work with Ali, Paul, and Volkan. So this talk is about sampling, which is a very fundamental task in machine learning, statistics, computer science, and so on. Let's say given a target distribution of the form e to the minus v, and we would like to draw samples from it. There's a very powerful framework in this regard that is called the Langevin dynamics. The idea is that you first set up a continuous time stochastic differential equation whose stationary distribution is precisely your target. And then you can try to simulate this continuous time dynamics by just discretizing it. And by doing so, you would acquire a very simple algorithm that looks like gradient descent plus some Gaussian noise. And as you can see, this algorithm is extremely scalable, and therefore is very suitable for modern machine learning applications. And the convergence rates of the Langevin-based algorithm are well studied for the case of log concave distributions in recent years. But this is under an additional key assumption that your target distribution is unconstrained, meaning the support of your target distribution is the whole space. However, there are many practically important distributions, such as the latent-Dirichlet allocation mentioned in previous talks before as well. They are actually constrained distributions. So the natural question is if you can extend this Langevin dynamics idea to sampling from constrained distributions. And this question turns out to be surprisingly difficult. And in fact, prior to our work, the state-of-the-art convergence rate for constrained sampling is significantly worse than their unconstrained counterpart. So sampling from constrained distributions seems to be a very challenging task. However, if you're an optimizationist, at this point you'll probably recall this very interesting example. So suppose we want to do minimization on the probability simplex. So this is a constraint optimization problem. But you actually know that there's an unconstrained optimization algorithm called the entropic mirror descent to solve this constraint optimization problem. The idea is that you don't directly do gradient descent because you have a constraint, but instead you're going to use the so-called entropic mirror map, the gradient of the entropy, to map your primal decision variable to the dual space. And then you can do gradient descent in the dual. And because of the key property that the domain of the differential dual of the entropy is the whole space, you know that your dual variable does not have a constraint, and therefore you don't need to do any projection. So based on this observation, we would like to ask whether this process can be replicated for Langevin dynamics, and the answer turns out to be yes. So given any target distribution, any mirror map, we can actually associate a dual distribution, and we can run Langevin dynamics in the dual to again ensure that the overall stationary distribution is your target. And once you have such a continuous time dynamics, you can simply discretize it to obtain an actual algorithm. And finally, because our dual distribution is unconstrained, our algorithm can inherit all the advantages of the unconstrained sampling, even though your original target is constrained. So based on the mirror descent framework, we're able to sharpen the state-of-the-art rates for constrained sampling. And furthermore, our theory reveals a very surprising phenomenon, which is sometimes you can actually turn non-convex sampling problems into convex ones. And this, in particular, includes the very important case of the latent Dirichlet allocation. So we're able to provide the first convergence rate here. And finally, because our algorithm is simple and it is unconstrained, it works very well in practice. If you have any further questions, I'll be welcoming you at poster number 43, along with my co-authors. Thank you very much.
Our next speaker is Pan Xu. He's going to talk about global convergence of Langevin dynamics based algorithms for non-convex optimization.
Hello, everyone. I'm Pan Xu from UCLA. This is a joint work with Jinghui Chen, Difan Zhou, and Quanquan Gu. In this work, we studied the global convergence of Langevin dynamics-based algorithms for non-convex optimization. Langevin dynamics is the following stochastic differential equation, where the drifter is the gradient of some smooth function f, and the diffusion coefficient is a constant independent of time. Here, beta is the inverse temperature parameter, and bt is a standard Brownian. Of stochastic process xt converges to a stationary distribution which concentrates on the global minimizer of f. Therefore, we can use long-join dynamics to design algorithms that converge to the global minimizer of a potentially non-convex function. Gradient long-join dynamics, or GLD, is the unit discretization of long-join dynamics. We prove that GLD converges to the global minimizer of the function f. To this end, we need to bound the optimization arrow. Previous work connects the discrete time process xk with the continuous time dynamics xt, and then with the stationary distribution of the long-join dynamics pi, which concentrates on the global minimizer x star. Then the optimization arrow can be decomposed as follows. The first term is the discretization arrow between the discrete time process and the continuous time dynamics. The second term characterizes how fast the continuous time dynamics converges to its stationary distribution. And the last term is the distance between the stationary distribution of long-join dynamics and the global minimizer. It is proved that GLD converges to a neighborhood of the global minimizer up to the model arrow after 1 over epsilon to the power of 4 iterations. This iteration complexity is rather high since they have a very large discretization error term. In our paper, we propose to directly study the convergence of the discrete time process to its stationary distribution mu, and then we bound the distance between the discrete time stationary distribution mu and the continuous time stationary distribution pi. And the third term is still the model error of the long-join dynamics. And we prove that GLD converges to the same neighborhood of the global minimizer after 1 over epsilon iterations. And the main advantage is that we do not need to bound the discretization arrow, and this is a big improvement from the previous results. We also prove that under the same decomposition schemes, the global convergence of SGLD and that of the variance-reduced SGLD, which is faster than both GLD and SGLD. And for more information, please refer to our paper and welcome to our poster at number 46. Thanks for your attention.
Our next speaker is Early Sherman. He's going to talk about identification and estimation of causal effects from dependent data.
Hi, everyone. I'm Eli, and this work is with Ilya Spitzer, both at Johns Hopkins. So we're interested in estimating causal effects from data on interacting agents. This could be online social networks, flu vaccines, infectious diseases, randomized trials on small villages that are otherwise independent. The major difficulty here, of course, is that the units in the data are dependent. So as kind of a thought experiment, consider this question. If your friend Sam jumped off a bridge, would you jump too? There's a couple reasons why you might decide to jump off the bridge. So maybe Sam's really cool. You want to imitate Sam so you can be cool too. That's a form of social contagion. Maybe Sam infected you with some judgment-suppressing parasite or disease, and that's a physical contagion. Perhaps you and Sam are both daredevils, and whether it's known or unknown to the analyst, this is some sort of homophily, so shared characteristics between the two of you. And finally, it could just be that there's sort of a Tacoma Narrows situation going on where the bridge is actually collapsing and you and Sam have to jump to survive. And in general, it's not possible to disentangle these different ideas, but under some assumptions, causal inference is possible. So bringing this closer to the present work, let's consider the following social network, which is represented by the graph on the bottom left. So subject I spends time on a social network, and that leads to purchasing behavior or maybe voting behavior, some political action. That's mediated by participation in some social network, which we represent by M, which is entangled through the social network with person I's neighbors. And then in addition, person I has some characteristics C and confounders H that confound the treatment and the outcome, treatment being time spent online, outcome is that purchasing behavior. So we're interested in answering this counterfactual question. What happens if we artificially set person I's time online? How does that affect person J's behavior? Excuse me. And of course, this query is complicated by a couple things. One is interference, where person I's treatment actually affects person J's outcome. Two is some symmetric dependence through the social network, and because all of the participation variables in the social network are connected, are marginally dependent, it's as if we have one sample. And then finally, we have confounding, again, between the treatment and the outcome. So a light intro to causal inference for those of you in the room who haven't seen much causal inference before. We typically are interested in comparing cases and controls. So we want to estimate some parameter beta that's the expected value of your outcome under the assignment to 1 for your treatment and the assignment to 0. Identification is this concept of whether or not we can actually estimate the parameter of interest from the observed data that we have. It's a fundamental problem in causal inference that we only observe the assigned, that is the observed treatment in the data set, and sometimes we don't have identification from our data. So for instance, in this example that I gave, if we observe all of the confounders, then we're identified. But if we're not identified, then we have some ill-posed problem, which no matter how large n gets, we still can't actually answer the counterfactual query. So we need models and assumptions in order to get identification. In our case, we use graphical models. So what types of graphical models do we use? We kind of go above. Many of you probably are aware of DAGs. We use a type of graph called chain graphs, which of course allow for directed relationships, as in DAGs, but also we allow for undirected relationships, which represent a feedback process between two variables. And then going beyond that, we allow for confounding between variables in a notion called segregated graphs. So in this paper, we talk about a complete identification algorithm, which basically takes in a graph and a counterfactual of interest and it puts out either an estimatable function, which you can estimate using conventional machine learning methods, or it'll output failure if we're in a non-identified case. So this graph up here demonstrates an example of non-identification. You see from, say, just consider person 1, A1 to Y1, there's both a directed edge and a bidirected edge, where bidirected edge represents that confounding, and we can't disentangle the effect versus the confounding. And this, of course, extends ID theory dating back to 2002 in Jintian and Yuta Pearl. So what are our contributions? Again, we have this. We present this complete identification algorithm in segregated graphs. The graph that I gave with the social networking example, this is what that estimable function looks like. Obviously, it's very complex. I'm not going to the details because this is a spotlight talk, but feel free to come to the poster. And then, in addition to that, we talk about how one might do single sample inference. So I mentioned along that social network, everybody is marginally correlated, and in essence, you have one sample. And so how might you do inference on that? We use an existing algorithm called the AutoG computation algorithm, and the experiments we use demonstrate that this algorithm gives consistent estimates. So again, devil is in the details. I glossed over a lot. Come to our poster. It's number 13 in the next session. Thanks.
Our next speaker is Joanna Mitrovic. She's going to talk about causal inference via kernel deviance measures.
Thank you for the introduction. So my name is Joanna, and this is joint work with Dino Sedinovic at Oxford and Iwaite at Oxford and DeepMind. So many scientific questions we here want to answer are actually fundamentally causal in nature. So might it be genetic drivers of some diseases, or if we're interested in the motives behind customers' purchasing behaviors. And for correctly addressing these questions, for properly answering them, we really need experimental data. And what do I mean when I say experimental data? Well, we need data from randomized controlled trials where we are able to control a lot of the variables except those we're actually interested in inferring. Unfortunately, often this data is just not available, and we're left with having to deal with observational data. Why this might be the case? Well, sometimes it's just not ethical to perform these experiments, or we might not have the financial backing, or sometimes it's just technically not impossible. I mean, if you're testing a drug, you cannot bring somebody back from the dead. And this kind of real-world limitation raises a very important question. We want to answer these questions that are very important for us to know the answers to, but we only have this observational data. So how do we do causal inference from purely observational data? Most of prior work can be kind of grouped into two categories. The first category relies on testing for conditional independence. In particular, you would start from the assumption that everything's causing everything, and then, so it's a fully connected graph, and from there you would prune away edges by testing a conditional independence between variables. Although this approach is very well mathematically founded, there are a few drawbacks. In particular, it doesn't give you a definitive answer. So often you would be left with many edges in the graph, many of them may be potentially unoriented. So you would be getting like a whole class of possible causal relationships instead of like one definitive answer, this is it. Second drawback is that these methods are often not very robust. So they're very dependent on whether your testing methodology is properly calibrated and how you choose the hyperparameters there. As kind of an answer to that, another line of research has emerged. In particular there, a particular functional relationship between variables is assumed, and they use what is called a symmetry between cause and effect. While this approach gives you a definitive answer, it is restrictive because you have to fix the functional relationship between the variables and the noise structure. So we examined this and we tried addressing these shortcomings. In particular, our contribution, kernel conditional deviance for causal inference, or KCDC for short, is a general purpose method which is fully non-parametric. It gives you a definitive answer, and you don't have to impose any a priori restrictions on the functional relationship between variables and the noise. So how do we manage to do that? Well, a short TLDR. First, we introduce a novel interpretation of this notion of asymmetry between cause and effect. In particular, we introduce something called minimal description length independence. And what is the intuition behind that? Well, the intuition is if you have a mechanism that generates the effect given the cause, the description length of this mechanism should be independent of the actual value of the cause you're putting in. Next, based on this symmetry, we provide a measure using kernel embeddings of conditional distributions, which is flexible and robust. In particular, you see here the formula of the KCDC measure, measuring structural variability in the reproducing kernel Hilbert space using norms of these conditional mean embeddings. Taking all of this together, we propose a causal discovery framework where we have 3 decision rules and a confidence measure. So you can either directly compare these KCDC measures to come to your answer. You can do majority voting by ensembling lots of these direct comparisons. Or, given that KCDC measures are particularly expressive in terms of the causal relationship, you can also use them as features within a classifier. And we also propose this confidence measure, which is the relative difference between the KCDC measures. We take KCDC and perform an extensive experimental evaluation against competing methods on a wide range of simulated data, and we achieve state-of-the-art on a benchmark dataset to begin cause-effect pairs. And if this is interesting, come visit us at poster 9, 210 room. Thank you.
Our next speaker is Nathan Kalus. He's going to talk about removing hidden confounding by experimental degrounding.
Thank you.
Hi everybody, my name is Nathan Callis. This work is joint with Alad Manaspuli and Uri Shalit. To motivate the problem that we're looking at, consider the following situation. A patient, Anna, has just been diagnosed with type 2 diabetes. By looking at her records, we can see what her current and past blood sugar levels have been, what's her age, weight, BMI, and many other covariates. The question then is, given all of these baseline covariates and goaded by the variable x that we know about the patient Anna at this point, what should be the first-line glucose-controlled treatment that we should give her? Should it be, say, insulin encoded by t equals 1, or should it be metformin encoded by t equals 0? Specifically, we're interested in what is the causal effect of giving one treatment versus the other, given all that we know. Therefore, we're interested in the conditional average treatment effect, or CATE, which is this function tau, which is equal to the conditional average of the difference between the outcome under one treatment and the outcome under the other, given all the covariates that we have. This question obviously arises in many other application domains, including medicine. The question then is how to estimate tau. The hope is to use large-scale observational data. We can, for example, extract the electronic medical records, or EMRs, of a variety of diabetic patients from the hospital's database, record what were their covariates at the time of their first-line treatment, what that first-line treatment was, and what was the outcome. Then, using this data, a variety of machine learning methods, including causal forests and TARNet, are trying to estimate what is the observed difference in outcomes. Specifically, what is the difference between the conditional expectation of outcome given x in the insulin population minus what is the conditional expectation of the outcome given x in the metformin population. Call this function omega. These approaches usually assume that omega is actually equal to tau, so that if we're interested in individual level causal effects, all we have to do is estimate omega from observational data and done. This, however, relies on the assumption that there's no hidden confounding after we control for x. Hidden confounding are the hidden correlations not accounted for in x between who got what treatment and why, and what are the particular outcome idiosyncrasies of any one individual. For example, we may have in the data that healthier patients tend to get metformin. Then, if we looked at the observed difference in outcomes, that might make metformin look much better than its causal effect really is. That is to say, omega would not be equal to tau. We can try and alleviate confounding by controlling for richer covariates, but when dealing with observational data, confounding is always going to be unavoidable to some extent. The way we usually avoid confounding is by running experiments. Experiments like A/B tests or clinical trials are going to be unconfounded by design. However, they're going to have limited generalizability, especially if we're using existing data from an experiment conducted elsewhere. They're also going to be prohibitively small, and therefore going to be limited in the number of samples that we can use. On the other hand, observational data, such as the ones derived from EMRs, although they're confounded by default, they're usually going to cover the population of interest because they're coming from your own hospital, say, and they often have much larger samples. The question then is how to get the best of both worlds. Therefore, the question that we asked in this paper is how might we use a small experimental data set with limited generalizability in order to remove the confounding errors that we would get from fine-grained estimates from very large-scale observational data sets. The method that we developed proceeds roughly as follows. First, use your favorite black box method, whether it be causal forest or TARNet, in order to fit this omega function, the observed difference in outcomes, on the observational data. Then we develop a new way to fit the difference between omega and tau, precisely the confounding error, call this eta, across the two data sets. Okay, so we compare the two data sets and learn what this tau is, the observational and experimental data set. We then remove eta from omega in order to return the grounded estimate tau. The main theoretical result in our paper is a guarantee that says that if eta is in a finite parameter class, if omega is consistently estimated, then so is tau hat will be a consistent estimator. This assumption that eta is parametric is strictly weaker than assuming that there is no confounding, which would assume that eta is precisely 0. We applied our method to an educational data set. Looking at data from the STAR experiment, we tried to estimate what would be the effect of large versus small classrooms on first graders' test scores. Our method, here in blue and in orange, outperforms the other ones. I hope I've piqued your interest enough to come to the poster and hear all the details of our work. Our poster will be on display for the next 2 hours on this floor in poster board number 2. Thanks.
Thank you for coming. And let's thank all the speakers again.